Good morning. My hair has gotten a little bit crazy. But yeah, good morning. Welcome to our second week. Sorry, I haven't looked in a mirror yet today. But yeah, today we're going to continue talking about limits. And this week we're going to start branching into the technical definition of continuity as we get ready to talk about derivatives. So give me just 1 second here. I'll get the .cam fired up and we can get started. Mostly this week is going to be about mastering those algebraic techniques that I introduced to you at the end of class on Friday. Okay. So we've been in chapter 2, which is all about limits of functions, and we're going to continue there this week. Mostly we're going to be working in 2.3, 2.5, and 2.6. So this week, .3 is calculating limits with limit laws. And we did a little bit of that last week. There's going to be a small amount of overlap between the stuff we were doing last week and the stuff we're doing this week. And that's intentional to kind of help round out those skills that may need a little bit more work from last week, so I can assign you some tougher problems from that section. But then we're also going to go on to talk about 2.5, which is on continuity. And I think we all have some idea of what it means for a function to be continuous, because we hear that word thrown around so much in math classes. But 2.5 is where we're going to actually introduce the technical definition of continuity that is in place for the earlier calculus classes, like Calc 1 through 3. And then we're going to talk about section 2.6, which is on limits at infinity. Which turns out to be the same thing as talking about horizontal asymptotes. So we'll be looking at what happens as you send x to infinity in 2.6. You notice we're skipping over 2.4. Which is on the technical, i.e. Epsilon delta definition of a limit. So you will hear people refer to epsilon delta proofs or epsilon delta arguments or epsilon delta definitions. It turns out that the way calculus works is that in order to prove the theorems, i.e. the little tools that we're going to use to calculate these limits, like all the limit laws that we introduced last time, requires imagining kind of kicking things a little bit and then watching how much they wiggle. So epsilon and delta, when you see this language, epsilon delta definition or epsilon delta proof or argument, means you give yourself a little bit of wiggle space. You say, I'm going to allow this thing to move by epsilon, and then I'm going to try and figure out the necessary constraints, and that's your delta, to keep your wiggle as small as epsilon. This is something you'll learn about if you choose to take so-called advanced calculus or real analysis, but it's not something that we spend a lot of time on here in Calc 1 because it's not really helpful. You know, when we say as x gets closer and closer and closer to a, does f of x get closer and closer and closer to L? That's how we define the limit, right? Well, getting closer and closer and closer means, you know, x getting closer and closer to a means x is within delta of a. And then f of x getting closer and closer and closer to L would mean f of x is within epsilon of L. So normally we think of these as two very small positive real numbers. And then we kind of build proofs using absolute value inequalities in terms of those things. But we won't spend any more time on this than I just spent. So this week we're going to talk about this stuff because those are the things that you need to become good users of calculus. This is something that you need to become a good prover of new calculus tools, but you don't need it to become a good user of calculus, kind of like the difference between coding your own software and learning how to use the software. So this is how we use it, and this is how you would code it if you had to, but you don't. So I want to return to 2.3 and start pretty much right away on just showing you more and more and more algebraic techniques to calculate limits. Before I start digging into stuff, is there anything from the homework that you guys would like to take a look at? Any problems that you're kind of stuck on or just feeling not completely satisfied about? So you can type them into the chat or you can hold down spacebar and just shout out. But is there anything that you guys would like to look at before I start grabbing examples? Carson, I'm seeing that you are speaking, but I can't actually hear you. Are you trying to say something? Try. Okay. So if there aren't any objections, then if there are no homework problems that anybody wants to see worked out, and again, if there are, take a second, you know, let me know what they are. If there aren't, then I'm just going to start grabbing more examples because there's so many more techniques. It's all the same sort of thing, right? It's all like do some algebra, factor, and cancel, and then plug in. That's always kind of the recipe for these problems. But
yeah, I have one, Professor. Just give me 1 second to pull it up.
Okay, sure, yeah. And Krishna's asking to do number 7. Well, let me save this. This is your homework for this week. It's not out yet.
I'm not sure if it's number 7, but whatever the problem that was had the tangent and sine function in it.
Oh yeah, I think we did that one in class last time, but we can run back through that quickly. Number 6 had the tangent and sine.
Yeah, I just wanted another example.
Okay, and then number 7, again, use a table of values. Okay. Number 8. All right. Yeah, all right, so 6, 7, and 8, let's do it. Number 6 has some randomness built into it. Your numbers might be different. This time when I generated the homework, this is what it looked like. That's it. 3 and 4. Okay, so they say to calculate this limit, the limit as theta goes to 0 of sine 3 theta divided by tan 4 theta by making a table. So what that means is I should plug in a bunch of theta values that are really, really close to but not equal to 0 and see if those numbers are getting closer and closer to anything in particular. So here's my theta, and over here I'll have sine 3 theta over tan 4 theta. So it's just going to be a table of values. I think last time I was using decimals. Now we'll do it like that again, sure. So we'll start with like 1 and then 0.5, like 0.25, and then maybe 0.1, and then maybe 0.01, and then maybe 0.001. So these theta values that I'm going to plug in are getting closer and closer and closer to 0, right? 1, 1/2, 1/4, 1/10, 1/100th, and 1/1000th. Those are the thetas that I'm plugging in. And so as you walk down this table, the theta values are getting closer and closer and closer to 0. And so I'm going to see if this function starts getting closer and closer and closer to anything as theta gets closer and closer and closer to 0. Now, to do these calculations, you will need a calculator, because certainly these are not numbers that you'll be able to crunch out by hand. So let me get my silly virtual TI-83 out. I'll move this off to the side so we can still see everything. So first we'll start with the 3 theta. So this will be the sine of 3 divided by the tangent of 4. That's plugging in theta equals 1. And I get 0.122. I'm going to round to 3 decimal places. Yeah, that's fine. And then if I plug in 0.5, that will be the sine of 3 times 0.5 divided by the tangent of 4 times 0.5. Which is negative 0.456. Is that right? Did I type that in right? 3 times 0.5, 4 times 0.5. Sure, okay. So that's negative 0.457, really. Around there. Next, I'll plug in 0.25. So that will be the sine of 3 times 0.25 divided by the tangent of 4 times 0.25, which is 0.438. And we're going to fill out this table and then see if we can guess at what these numbers are getting closer and closer to. So my next guy would be sine of 3 times 0.1 divided by the tangent of 4 times 0.1. It's like 0.699. I'll have my next row is theta equals 0.01, so that'll be sine of 3 times 0.01 divided by the tangent of 4 times 0.01. And this is 0.749. Okay, so these are starting to get closer to something. 0.4, 0.6, 0.7. And let's see, if I look at theta being 0.001, then I'll have the sine of 3 times 0.001 divided by the tangent of 4 times, yeah, not typing on this thing, 0.001. That's 0.74999. Let's do one more. Let's let theta be 0.00001. 0, 1, and see what we get, just to see if we're getting at what we want to. So I'll take the sine of 3 times 0.0001, and I'm going to divide that by the tangent of 4 times 0.0001, and we get, so I apologize, I'm rounding differently here, 74999. 1, 2, 3, 4, 5. Okay. So as my theta values get closer and closer and closer to 0, this function's values, at first they don't appear to be doing anything interesting, but then starting right around here, they start sneaking up on this 0.75 number, right? So as theta goes to 0, it appears that sine of 3 theta over tangent of 4 theta is getting closer and closer to 0.75. All right, that's what these numbers are getting closer and closer and closer to. 0.7499999 is really close to 0.75. And the closer I let theta get to 0, the closer this output is getting to 0.75, or 3/4. All right. And that's no coincidence. The relationship between the value of this limit and the two numbers that you see inside the trig functions there are what they appear to be. And that's something we'll be able to prove eventually.
That was my second question, because I think mine was sine 5 theta over tan 4 theta or something like that, and it ended up being 1.25. So I was going to ask if it was just coincidental or.
Definitely not coincidental, no. And then I also got a question here in chat asking, if I gave this question on a test, would you be able to use a calculator? I would never give this question on a test. And by the time we get to our test, you will have the tool that you need to prove this directly. So this is one of our very early questions where you're kind of meant to experiment and play around a little bit as you get a feel. But if I were to give you a question like this, I would give you the necessary tools or table. Like I might give you a table like this and ask you, what does that limit appear to be approaching? But I wouldn't make you do a calculation like this on a test. And if there was a calculation intensive problem like this, I suppose I would have to provide a calculator, but that's not the sort of thing that I aim to test you on in this class. I aim to test you on your calculus skills. So we'll not have to worry about the test thing. And yes, the relationship is what it appears to be. I do have one last little thing to say about this, or maybe question to ask you guys before we leave here. This table, is it really investigating this limit, or is it investigating one of the one-sided limits?
One-sided limit, right?
Yeah, one-sided.
Yeah, really here I'm only approaching 0 from the right or from the left?
From the right.
Yeah, because these numbers are all positive, right? So if I wanted to be really careful, and this is the sort of thing that I'd like you guys to be thinking about as you write out your homework. When I write this sentence here, so as theta goes to 0, it appears that da 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 goes to 0.75. Really what my table tells me is that as theta goes to 0 plus sine 3 theta over tan 4 theta appears to go to 0.75. Now it turns out that this function is a ratio of two odd functions, which means it is automatically an even function, which means that this table would be identical if I changed all of these to their negatives, all the theta values to their negatives, the outputs would be the same. So I'm not going to take the time to go through and rebuild that table, but if I wanted to do this very carefully, you would not only need these theta values, but you would also need their negatives to make sure that as you sneak up from the left or from the right, that you're ending up at the same output, 3/4. Okay, we did do this a little bit more carefully in Friday's video last week. So if you'd like to see this done with the two-sided approach very carefully, go ahead and rewatch the video from last Friday. Any other questions or comments on this problem before we move away from it?
No, sir.
Anybody else?
So was I supposed to write all this as an like answer in the WebAssign too, or just the answer worked fine?
Well, I think WebAssign probably only gave you the space to write the answer.
Yeah.
But you see here they say use a table of values to estimate the value of the limit. And right now we don't really have any other way to try and figure out what this limit is. So in order to solve the problem, you would have to make a table like this. You don't have to use exactly these theta values, but you do need to plug in some theta values that are close to 0 and try to see what the outputs are getting closer and closer to. But then in WebAssign, yeah, they just want this answer. They just want 3/4 or 0.75.
Okay, thank you.
Of course. All right, so we wanted 6, 7, and 8. 7 is kind of similar. So estimate the limit. Via a table. Okay, so this is what I'd like to do. I'd like to estimate the limit as x goes to 0 from the right of x to the 4 times ln x. I didn't say it as we started the last one because we've worked that problem before, but what's wrong with just plugging in 0 here?
Undefined.
Yeah. If I do that, then I get 0 to the 4 times the natural log of 0. What's wrong with that? Why is that undefined?
Because it approaches infinity.
Yeah, that's the idea. This guy doesn't exist, right? This is undefined. Remember, any sort of logarithm has domain just positive numbers. You can't plug in 0 or anything smaller than 0. The graph of the natural log is one that you should know. I understand that not all Calc 1 students come into Calc 1 having remembered this, but please, please, please get this graph in your head and never forget it. It's one of the most important ones. We go through this point, 1, 0. Out here at E, we go through the point E, 1. And then here, as you approach 0, there's a vertical asymptote, right? The natural log dives down to negative infinity. So this is the graph y equals ln x. And it's one that we need to know. We need to know it well. So it's the natural log piece here that is causing us trouble, right? As x goes to 0, this looks like 0 to the 4 times negative infinity, which is definitely not well defined. So a table of values is going to be the way to go. And I'll attack it the same way we did the last one. I can't plug in 0, but I can plug in 1, 0.1, 0.01, 0.001, and maybe 0.0001, and see what those outputs look like. Here they only asked for the limit as x goes to 0 from the right. Why didn't they ask for the full two-sided limit? Why did they ask me to look at the limit as x goes to 0 plus?
Because it has a vertical asymptote? No.
The function doesn't exist on the other side, right?
Yeah, there is no piece of the natural log graph over here. I can't plug in any negative numbers to this guy. The ln of -1, -0.1, -0.01. The ln of any of the negative versions of this is going to be undefined because the ln function has domain just positive numbers, right? So I can't actually plug in any negative numbers. This function, his domain is the open interval 0 to infinity. So this is the best I can hope for, right? There is no chance of a two-sided limit here, because the limit as you approach 0 from the left can't even be discussed, because this function cannot take any negative inputs, and any number that is to the left of 0 is automatically negative. Okay, so move this over here this time. When x is equal to 1, you'll have 1 to the 4 times the ln of 1. That's 0, because the ln of 1 is equal to 0. And for the rest of these, I will need the calculator. So we're going to have 0.1 raised to the 4. And then I need to multiply this. Here, let me use some better notation, right? So we should really have this as parentheses 0.1 close parentheses raised to the 4 times, and now the ln of 0.1. So I don't know how familiar you guys are with scientific notation, or what it is that we're looking at here. This e right here stands for exponent, but it's not the same as the base of the natural log. They use a capital E. So the way I would write that down, that's scientific notation. It's negative 2.3, I'll just round it there, times 10 raised to the negative 4. And this piece, the 10 to the negative 4, is what this e negative 4 means. So this is called scientific notation, and it's a convenient way to write very, very large or very, very small numbers. If I wanted to write this out in full decimal terms, this would be negative 0.000, that's 23. If I look at x being 0.01, so I'll type here 0.01 raised to the 4 times the natural log of 0.01. This is negative 4.6 times 10 to the negative 8. Which is negative 0.000000046. That's correct, right? Yeah. You can kind of get a feel for what's happening here. Are these large numbers or are these small numbers?
Are they actually
Super small.
smaller?
Yeah, they're insanely small, right? Like 0.000004. That's a very, very small number. We'll do one more. I think I might not need this guy to make a reasonable conjecture. So for our last input here, let's look at 0.001 raised to the 4 times the natural log of 0.001. Yeah, negative 6.9 times 10 to the negative 12. If you're wondering how I'm going from the scientific notation to the decimal notation, this exponent tells me how many zeros, right? So there's 1 0 before the decimal place. And so overall here I've got 8 zeros, right? 1, 2, 3, 4, 5, 6, 7, 8, because it's 10 to the negative 8. So if I wanted to take this guy from scientific notation back to regular decimal notation, this would be negative 0. I count 11 more zeros now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then the 6, 9. So these are extremely small numbers, right? These are numbers which are very, very close to 0. So this limit is starting out here as x gets closer and closer to 0, right? 0.1, the output is this. 0.01, the output is this. 0.001, the output is this. These numbers are very quickly, these outputs are very quickly getting closer and closer to 0. The limit lim x to 0 plus x to the 4 ln x appears to be 0, because as x gets closer and closer to 0 from the right, these outputs are getting closer and closer to 0. They do say we can confirm this graphically, and I think it's always a wise move to do that. So let's take a look at the graph of this function. The graph I drew for you there was just ln x. We want x to the 4 times ln x. I don't know what that graph looks like off the top of my head, but Desmos does. Ooh, a little funny, right? So what's going on in here? The natural log, he wants to go down to negative infinity. He wants this graph to explode way down here. But the x to the 4 term, he wants to go to 0. And he's stronger than this. X to the 4 wants to go to 0 more than ln x wants to go to negative infinity. Does that make sense? We can take a look at a different scale graph in Wolfram. Sometimes this does a better job of pointing out the interesting shit. But I don't think we're going to get a much more insightful picture than we have there from Desmos. Yeah, so here you did zoom in on that kind of little bloop, right? We've got this little bloop here, and Wolfram kind of zoomed in on it. So here you see this bloop, this going down here. This is the natural log for just a second winning, starting to make this thing go down to negative infinity. But then the x to the 4 term, as your x values get closer and closer to 0, that x to the 4 term wants to go to 0 a lot more strongly than the natural log wants to go to negative infinity. So the x to the 4 term is winning. Wolfram always writes the natural log as log. It's not an uncommon notation you see down here. It stands for the natural logarithm. A fun question would be, what about x cubed? Same sort of thing, right? Or x squared. And you can see as the power of x gets smaller, this dip gets deeper. Because x squared doesn't want to go to 0 as fast as x to the 4 does. So the natural log wins a little longer. But eventually, even x squared goes to 0 harder than ln goes to negative infinity. What if I just look at x times ln x? Well, again, that dip has gotten bigger because the natural log really wants to go to negative infinity. But he still doesn't want to do that as bad as x wants to go to 0.
So like,
limits would end up being 0.
I have a question.
Yeah.
So the numbers on top of the axis are almost like fractions to this graph. They tend to like curve at a slower pace or a minimum pace versus if they were like, you know, closer to 1, they have a tendency of like making a bigger hoop, like a faster rapid movement to 0. I don't know if that makes sense. Sorry.
Good. This is exactly what I want you guys to be thinking about. So let's look at a few of these together. All right. So red, blue, green, purple. The powers of x are getting larger as you go up, right? On the graph over here so the red has the smallest power of x, the blue has the next smaller power of x, then the green, then the purple. Compare this to this. Let me just look at x, x squared, x cubed, and x to the 4. Okay, and let me zoom in similarly so that we're looking at the same sort of piece of the graph. Okay, So x, x squared, x cubed, x to the 4, right? Notice how these, as your x values get closer and closer to 0, x to the 4 is the flattest on the bottom. Those outputs get closer and closer to 0 faster than the outputs for this red guy, right? Like for example here, when x is 0.2, the red guy is way up here. But the purple guy, he's practically 0 already. He's very, very close to 0 already. So the purple guy, x to the 4, he's trying to sit down on the x-axis much harder than the red guy. Harder even than the blue or the green guys. Same sort of thing is happening here. The red guy, because he has a lower power of x here, that's a lower multiplicity root at 0, he isn't trying to sit down as hard as the purple guy, who's trying to sit down super hard because that power of x is large. The basic idea is this: if you take a number that is between 0 and 1 and you raise it to a large power, that number will get smaller. Think about 1/2 squared. That's 1/4, right? It's smaller than 1/2. 1/2 to the 5, that's 1/32. That's way smaller than 1/2. So as you take numbers that are small, i.e. between 0 and 1, and you raise them to larger and larger powers, they want to go to 0. So here I'm thinking about plugging in x's that are between 0 and 1, because I'm talking about the limit as x goes to 0 from the right. So I'm talking about plugging in small positive numbers. Each of these polynomial terms, x, x squared, x cubed, and x to the 4, treat those numbers a little bit differently. Like imagine I plug in 1/2. In this red guy, the x term is just going to be 1/2. In the blue guy, the x term would be 1/4, which is much smaller, right? And notice that this blue graph is about twice as close to the x-axis as the red graph. Why? Well, because this is like 1/2 and this is like 1/4. The x cubed term, he's going to be even closer to the x-axis, because if I take 1/2 and I cube it, that's going to be smaller than what I get if I take 1/2 and I square it. And then same sort of pattern holds true here. Now the natural log, he's messing up the numbers, right? He's making everything negative because the natural log of a number between 0 and 1 is negative, and he's also affecting the size of the number a little bit. But really the thing that dominates, the term that overall dominates the behavior of this function or this family of functions near 0 isn't the log term, it's the polynomial term. This is something that you can explore really deeply. It's called asymptotics. And in Calc 2, we'll talk about it a little bit, if you take Calc 2 with me. But basically, polynomials are stronger than logarithms. Logarithms are kind of weak boys. Polynomials are kind of like, tough guys. So they're like, I want to go to 0. And this guy's like, no, I want to go to -infinity, but he's stronger. So we go to 0. Does that make sense?
Yes.
This stuff is a little bit heady and it's going to take some getting used to. And looking at lots of graphs like this is a really good way to start to develop that intuition. So why was this limit 0? This limit was 0 because the polynomial term x to the 4 really wants to go to 0 as x goes to 0. He wants to go to 0 really hard. And so he takes over. Right? He pretty much ignores what the natural log wants to do, and he takes over and says, nope, we're going to 0. We're going to 0 fast. And that's what happens, even though the natural log term dives off to -infinity. So any questions on how we solved this problem? I know we had a lot of discussion there, but this process of like writing the table and coming up with this idea that the limit is 0, any questions on how we did that? Fair question. So what if we were trying to go somewhere other than 0? Turns out 0 is the only interesting place for this function. 0 is the only number that I can't plug in, but I can get close to for this function, right? If you plug in any positive number, if I was looking at the limit as x goes to 1 or 2 or e or 5 or 10, all of those limits I could get just by plugging in. But 0 is the only place where this function is undefined, but I can sneak up on it. So the domain, so a little continuation of the why can't I plug in conversation. The domain of f of x equals x to the 4 times the natural log of x is the open ray 0 to infinity. And f of x is continuous everywhere in its domain. So if I wanted to take the limit as x approaches 1 or 2 or 5 or 10 or e for this function, I could just plug that number in. That wouldn't be too exciting. There's nothing hard to do there. So the only number that is kind of interesting to investigate using a limit for this function is 0. And that's because 0 is not in the domain, but it's the boundary of the domain, right? So I can plug in numbers that are very, very, very close to 0, but I can't plug in 0 itself. That's what makes this an interesting limit to investigate. And any other number doesn't have that property for this function. So good questions. Is there anything else that we're kind of wondering? Okay, I think there was one more question from the homework that you guys wanted to look at, and then we will return to these algebra tricks. Number 8, right? Determine the infinite limit. Yeah, so we haven't talked too much about this. Let me. This is all very intuitive. It does exactly what you think it does. So this is the limit as x approaches 1 of 2 minus x over x minus 1 squared. Okay. There we go. Again, we should ask, well, can I plug in x equals 1? And again, the answer is no, because if you try to plug in x equals 1, you get 1 over 0, right? 2 minus 1 is 1. 1 minus 1 is 0. So we can't just plug in x equals 1. In other words, and here's a notation I like for this. This looks like 1 over 0. So you'll see me use those quote bunnies a lot, right? The little symbols to say, I'm not responsible for this. In other words, this is what I get when I just plug this number in to this expression. This is undefined, of course. Can't divide by 0. But we can start to think about limiting cases, right? And I think the easiest way for us to do this right now is going to either be by looking at a graph or by making a table. The graph of this function is one that we should be able to conjure. You all took pre-calculus. This is a rational function. So without using any graphing software, who can tell me a little bit about the graph of this function? Who can tell me any features of the graph of this function? You guys remember how to graph rational functions from your pre-calculus class? We want to find all the asymptotes. We want to find all the intercepts. So here the degree of the top is, the degree of the bottom is 2, and the degree of the top is 1, right? It's a rational function, which means the top and bottom are both polynomials. The bottom is a quadratic polynomial, the top is a linear polynomial, which tells me that the horizontal asymptote is the line y equals 0. The top is equal to 0 when x is equal to 2. So maybe I'll mark this as 1. I'll mark this as 2, which means I have an x-intercept at the point 2, 0. The bottom is equal to 0 when x is 1, which means I have a vertical asymptote, x equals 1. And then to get any sort of feel for what the rest of this function is doing, I would need to plug in a few numbers. If I plug in 0, that will give me my y-intercept. So what happens if I plug in x equals 0? Well, then the top is 2 minus 0, and the bottom is negative 1 squared. That's 2 over 1. So that's 2. So what's going on here is I have a function that has a horizontal asymptote y equals 0, which means he's sitting down like that out there. He doesn't have any x-intercepts through here, so since this is positive, he has to stay positive, meaning he's going to approach this vertical asymptote like that. And then since this vertical asymptote is coming from a multiplicity 2 factor of the denominator, he won't change sign as you hop over the VA. But he does have this x-intercept here, and then he comes back and settles on this horizontal asymptote like that. So here's a good sketch of the graph of this function. Now, based on this graph, what happens as x approaches 1? If I'm,
It goes to infinity?
yeah, we're going up to plus infinity. So from the graph, we see that both the limit as x approaches 1 from the left of f of x is plus infinity, and the limit as x approaches 1 from the right of f of x is plus infinity. Therefore, the limit as x approaches 1 without any direction of f of x is plus infinity. What I did there to draw that graph, finding the asymptotes and the intercepts, that's an important skill that I know is sometimes a little bit overlooked in pre-calculus. If you took pre-calc with me, then I'm sure you remember all this talk of the multiplicity trick, drawing graphs, solving inequalities, all that good shit. You might remember it as just being something that you really hated and you're glad was gone. But it's back and it's really never going to be gone. It's always going to be important. So it's important you internalize that stuff. And if you want a little bit more practice with sketching graphs of rational functions, I recommend checking out Paul's online notes. I think he has a good page for this. If not, I can find something for you. Rational functions, practice problems. This might be decent. These are polynomials. There's some rational function stuff in here. Okay. Slant asymptotes, vertical asymptote, and behavior. No real talk of multiplicity stuff here. So if you, I'll need to search for a little bit. If you want a review of how to graph rational functions, like how to draw this graph by hand, send me a Canvas message or an email, and I'll dig up some resources and send them to you, since I don't see any in the obvious places, at least not right away. You can always verify. Desmos is your friend, so don't be afraid to use it. Let's verify. Oh, 2 minus x, not x minus 2. And then zoom, 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 zoom. Yeah, just like we thought, right? So at x equals 1, the thing blows up. At x equals 2, we cross the x-axis, and we dip down for a little bit, but then we come back up. And over here, we always stay positive, and we just settle down on the x-axis. In particular, as I walk along this graph, getting my x values closer and closer to 1, my y values blow up to plus infinity on both sides.
I have a question.
Yeah.
You instinctively knew there was a dip. How did you know there was a dip?
Good question. Because I know that this has to approach the horizontal asymptote over here. And I know that it had to pop through the x-axis here. So in order to pop through the x-axis, but then also approach this, that means I had to come down, but then come back up. So it's kind of a, I'll show you how I would, if I was trying to teach that process to somebody, how I would do it. So I draw in my asymptotes. Like this. And then I say, okay, well, my y-intercept here at 2 is positive. And I don't have any x-intercepts over here. So because I know my y-intercept is positive, and I don't have any x-intercepts over here, that means I need to be sitting down on my asymptote on the left from above. And then I'm going to have to cross here because this is a y-intercept, so I got to do something like that, which means that I'm going to approach this asymptote like this. Rather than down here, it's got to be going up there. Now this asymptote came from a multiplicity 2 factor downstairs, and an even multiplicity factor downstairs means you will not change sign. So if you leave going up, you're going to return from up, like that. Then I have my x-intercept over here at 2, 0. And since he came from an odd multiplicity factor, the 2 minus x factor upstairs here is an odd multiplicity factor. It's a multiplicity 1 factor. That tells me he's not going to bounce off of the x-axis there. He's going to cross the x-axis there. And then finally, that tells me that I'm going to be negative over here. So I have to approach this horizontal asymptote like that. So I start with this framework, and then I connect all the pieces. So I'd say, okay, well, now I know that I'm going to connect this like this. I know that I'm going to connect this down here to this. And to answer your question, I know I need to connect this to this. And I know I don't have any other x-intercepts in here. So that means I might come down here and fart around for a minute or do whatever, but I gotta somehow join back up with that, which means gotta be a dip. So like I said, if we want to talk more about just how to graph rational functions, I'd be happy to do that. But since it is a pre-calc thing, it's something that we should probably do in office hours or via emails, Canvas messages, videos, that sort of thing. But yeah, getting good at sketching graphs of rational functions follows the procedure that I just outlined. Factor the top and bottom. That'll tell you any x-intercepts and any vertical asymptotes. Plot the x-intercepts. Plot the vertical asymptotes. Make note of the multiplicity. So this was an even multiplicity thing. This is an odd multiplicity thing. Odd multiplicity means you're going to change sign. You're going to go from being positive to negative. Even multiplicity means you're not going to change sign. So for us here, the even multiplicity of this vertical asymptote told me I left positive, I'm going to come back positive. Here, the odd multiplicity of this x-intercept told me, oh, well, I'm going to come in positive. That means I need to leave negative. And that's the basic idea. I'll make a little note here to try and find resources on graphing rational functions. And post to Canvas. So we have a module in Canvas right now of review material. When I find something good about this stuff, I will post it there. Okay, was that, I think that was the last of the homework problems that we wanted to see. Is there anything else like that in here we should worry about? No. Okay, so then I want to talk with you guys, oh, why is this not working? A little bit more about the kind of technical or algebra tricks that will allow us to calculate more and more and more of these wonky limits. Last time we looked at a few basic limits involving rational functions where the denominator was going to 0. And then our very last example was one of those h goes to 0 limits. It looked like a difference quotient. So I want to return to a few problems like that and then look at some more challenging versions of those sneaky algebra tricks. So where are we? Yeah, this was the last one that we did. So let's look at, maybe I should say first, recall. How did we calculate the limit as h goes to 0 of 3 plus h squared minus 9 over h? You guys remember this problem from last Friday? It was the last one we did. How did we find this limit? What was the trick?
You make a table?
Not for this one. So our goal
Get rid of X on the bottom. Oh, H.
rid of the h downstairs, right? Here's the problem. If I just plug in 0 for h, then upstairs I get 3 squared minus 9, which is 0, and downstairs I just get 0, which is 0. So the problem is the h downstairs. So what we did is we did some algebra. I FOILed that out and factored and canceled until the 0 downstairs went away. If I FOIL out the 3 plus h all squared, we get this. And then the 9s eat each other up. I've got a plus 9 here and a minus 9 here. So I had 6h plus h squared all over h. And then I could factor an h from the top and cancel it. Important comment here, we can only cancel things top to bottom if we can factor them from both the top and the bottom. So it's only at this stage, after I factor out the h, that I can cancel it with the bottom. And I can't cancel these two. I can cancel these two, right? Because this guy is a factor of the top and this guy is a factor of the bottom. The bottom is really h times 1. So I can cancel, and we get lim h to 0 of 6 plus h over 1. And now I can plug in 0. This is just 6 plus 0 over 1, or 6. So that's the basic process, is whatever factor in the bottom is going to 0, you need to cancel that in order to take your limit. And so the next few problems I'm going to look at are all going to be like this in nature, where we're going to have to do some sneaky algebra in order to cancel a problem factor from the denominator. Then we'll be able to take our limit by plugging in. So the first new one I'd like to look at, if you want to see this again in careful detail, just go back to the video from last Friday. I would like to look at the limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. this has the same sort of issue as the last limit, where if I plug in 0 for t, the top is square root of 9 minus 3, that's 0. And the bottom would just be 0 squared, which is definitely 0. So somehow I need to get rid of the t squared downstairs. I cannot cancel this t squared with this t squared, because this t squared upstairs is not a factor of the numerator. I would need to be able to factor the t squared all the way out from the top, meaning every single term up there would have to have a t squared in it before I can cancel. So just like last time, we had to FOIL out that one piece before we were able to factor and cancel. We're going to have to do something here. We have to do some sort of algebraic manipulation before I'm able to factor and cancel. When I see an expression like this, where one of the numerator or the denominator is the square root of some variable shit minus a constant, my first thought is to multiply by the conjugate of that expression. And that's what we're going to do here. So I can't just plug in 0 because this looks like, right, and there's that notation, this looks like 0 over 0, which is undefined. This is what's called, remember, an indeterminate form. So instead, I'm going to have to do some algebra. And we need to be good with our notation. Don't skimp on writing the limits. Don't skimp on writing anything. Your hand will get sore. You'll use more paper. Be tough. Deal with it. Trust me, it's the right way to go. The trick that works here, I can't like FOIL this out. There's nothing to FOIL there. It's a square root. And I definitely can't give the square root to the t squared and 9 separately. Square roots do not play nice with addition or subtraction. But what I can do is multiply by the conjugate. So the conjugate of that numerator is what you get when you replace this minus with a plus. So that's the square root of t squared plus 9 plus 3. And if I'm going to multiply that upstairs, I need to also multiply that downstairs so I don't change the value of the function. So this is what we're going to do. This expression right here is equal to 1, right? It's something divided by that same thing. So I can multiply by that. That's not going to hurt anything. It's not going to change anything. But when I distribute upstairs, something nice will happen. I guess I should add here an important note. The square root of t squared plus 9 is super duper not equal to t plus 3 or anything like that. We can't do that. That doesn't work. That's something that I know a lot of people are tempted to do, but it just straight up doesn't work. That's not how square roots work. So instead we do this. And the way we do this, we FOIL upstairs. And downstairs we just leave it as it is. So this will be the limit as t goes to 0 of a big fraction. Downstairs will be t squared times the square root of t squared plus 9 plus 3. And those parentheses are important. Upstairs, I'll have to FOIL. I think of like this as these two big square roots. These are my firsts. These are my inners. These are my outers. These are my lasts. So when I multiply my first, I have the square root of t squared plus 9 times the square root of t squared plus 9. So I guess I'll just once, I'll write all this out in its gory detail. So this is root t squared plus 9 times root t squared plus 9. And then my inners are minus 3 times root t squared plus 9. My outers are plus 3 times that root, plus 3 times the root of t squared plus 9. And then my lasts, minus 3 times plus 3, that's minus 9. Notice that the inners and outers cancel. So this and this are all that's left. in the numerator. So I get lim t to 0, the square root of t squared plus 9 times the square root of t squared plus 9, just like the square root of 5 times the square root of 5 is 5. This is just t squared plus 9. These two middle terms add up to 0. And then that very last term there is minus 9. So this is what I have. And the denominator hasn't changed. Now the plus 9 and minus 9, those also add up to 0. So this is equal to the limit as t goes to 0 of t squared over t squared times the square root of t squared plus 9 plus 3. And now, having done all of this algebra, t squared is a factor of the top and of the bottom, right? That numerator t squared is really t squared times 1, and I can cancel, and I get lim t to 0, 1 over the square root of t squared plus 9 plus 3. And now as I send t to 0, the bottom no longer looks like 0. If I send t to 0, I get 1 over the square root of 0 squared plus 9 plus 3. That's 1 over the square root of 9 plus 3. Well, the square root of 9 is 3, so this is 1/6. And this, just like the last two examples that we've done, are very classic examples. This multiply by the conjugate trick that we used right here, common trick. So take a second, look at your notes, get your notes all caught up. So the first step here, where we actually did anything, right? The very first thing I wrote down is just what we get when we plug in 0. When we plug in 0, the top and bottom are both 0. 0 over 0 is undefined. So this shit doesn't work. Cannot just plug in t equals 0 at the start. However, I recognize this as being the shape of something that will respond well to this multiply by the conjugate trick. And that's something I know just from experience. I know that if I take an object like this, the square root of something minus something else, and I multiply by the square root of that same thing plus that same other thing, that there will be a lot of nice cancellation. It's really like a difference of squares thing here that's going on, but it's okay if you don't see it as that right now. This expression, root t squared plus 9 plus 3, is called the conjugate of this expression, root t squared plus 9 minus 3. If you have the square root of some shit plus or minus some other shit, then the conjugate of that expression is what you get when you flip that minus to a plus or that plus to a minus. So the square root of a plus b has conjugate square root of a minus b. And if you multiply these out, these always come out really nice. This will be root a times root a, which is a, plus b root a minus b root a, those cancel. This is always going to be a minus b squared. So there's a lot of nice cancellation that happens when you multiply by the conjugate. And knowing that ahead of time is what told me to go ahead and do this. I wanted to multiply the top by his conjugate, which means I also need to multiply the bottom by that, right? Just like when you're having a common denominator in fractions, you have to multiply the top by something, you have to multiply the bottom by something, so you also multiply the top by it. You can multiply by any number as long as you multiply on the top and the bottom. So I wanted to multiply the top by this, which means I also need to multiply the bottom by this. Upstairs, when I FOIL these out, right, this is like this times that. I FOIL everything out. This is what I get. Downstairs, I just write it as t squared times this. There's no need to distribute or anything like that because my goal is to cancel this t squared, remember. After foiling everything out and canceling everything that I can cancel, I get t squared over t squared times this. The t squareds cancel, which means I'm now free to plug in 0 because the t squared downstairs is what was giving me the problem. When I plug in 0, I get 1/6. So this, again, this is called multiplying by the conjugate. It's a very common trick, and it's one that we should practice. There's several problems in this week's homework, which I'll release immediately after class, that let you practice this, make you practice this. So make sure that everything I have here, you have in your notes. That way you'll be able to look back at this example when you work on the homework, and after you practice it a few times, it'll all start to make a lot of sense, I promise. So the most important thing for you to do right now is to make sure your notes are clear, readable, and have everything that I have here. So we'll take a second to do that. And then as you're doing that, think of questions you'd like to ask. Why did we do this? Or why did that come out like that? And then ask those questions.
I don't see the last two steps.
Sorry, here.
Square root of 9 plus 3. I mean, like, I don't see the mechanical steps. Like, how did we jump from 1/6?
Oh, well, the square root of 9 is 3. So this is 1 over 3 plus 3. And
Oh, okay. Okay. All right. Thank you so much.
we think so hard about the algebra, it's easy to lose sight of the arithmetic. It's not a stress. What else are we wondering? Okay, so this is where I'm going to put away this example for now. If you need more time with this, then of course just rewatch the video. You can pause, you can rewind, you can go back and forth. And if you have questions, don't be shy about sending me a message on Canvas. Normally I would say we could talk in office hours today, but I'm actually going to have to cancel today's afternoon office hour because I need to take my cat to the vet. But if you do have more questions about that example after you've looked at it and played with it a little bit, don't hesitate to send me a Canvas message. There are two other things from section 2.3 that I need to talk with you about. And these are both theorems that are pretty important. So the first one doesn't have a name, but it's important or helpful in understanding the second. If f of x and g of x are two functions defined near A, and for all x satisfy f of x is less than or equal to g of x, then the limit as x approaches A of f of x will be less than or equal to the limit as x approaches A of g of x. So in simple terms here, limits respect inequalities. If f is smaller than g, then the limit of f is smaller than the limit of g. That's all. the reason for these, defined near A and for all x satisfy statements, we need to make sure that I can talk about these limits, which means I need to be able to have, I need functions who have, whose domain includes all the numbers near A in order to discuss that limit. But you could think of it just as saying, if this, then this, if you want to. That's the theorem in short. If f is smaller than g, then the limit of f is smaller than the limit of g. This theorem is useful in understanding the following theorem, which is called the squeeze theorem. In France, they call this the policeman theorem. I'm a big fan of the French characterization of this theorem because it's really cute. It goes like this. Suppose you're walking down the street and there's a policeman in front of you and a policeman behind you. If both policemen are going to the police station, you are also going to the police station. In mathematical terms, it says this. If let's write it like this. If f of x is less than or equal to g of x is less than or equal to h of x for all x near A, then lim x to A f of x is less than or equal to lim x to A g of x is less than or equal to lim x to A of h of x. And in particular, so let's pause actually here for a second. So far, what I've written here is just the natural extension of this to three functions. If f is less than g, then the limit of f should be less than the limit of g. And if g is less than h, then the limit of g should be less than the limit of h. That's just what the previous theorem says. But in particular, if the two outside limits are the same, if the limit as x approaches a of the left function f of x is equal to the limit as x approaches a of h of x, say they're both equal to some number L, then L is less than or equal to the limit as x approaches a of g of x is less than or equal to L, which can only be true if the limit as x approaches a of g of x is equal to L. So if the two outer functions, the function that bounds you below and the function that bounds you above, both go to the same place, then the middle guy, u, are also going to that place. So here f is the policeman behind you, h is the policeman in front of you. And if the policeman behind you is going to the same place as the policeman in front of you, then you're also going to that place. Does that make sense? So again, I'd say make sure that you get down in your notes everything that I'm writing here. These two theorems are important. We're going to use them again and again this semester. I'll give you a couple seconds to finish writing the stuff down, and then I'm going to draw a picture, which should go next to this in your notes, and then we'll look at an example or two before class ends. Oh, we are right up out of time, aren't we? Yeah, so let me just give you that picture, and we'll start looking at examples next time. Maybe here's A. And here's my function f of x. And maybe my function g of x is doing some weird shit, I don't know. And then up here is my function. So I'll have him do something like this. There's g of x. And up here is my function h of x. G and then h. And the idea here is that this is just one point right here. So this function g might be doing some weird stuff, and it might be really hard for me to say what's going on. But if the other two functions both go to the same y value, L, then the weird behaving guy in the middle also has to go to L. I can probably get you a better looking picture than that over here. Yeah, this is the idea. That's that delta epsilon stuff, though. I don't want to scare you. Here's a reasonable picture for the squeeze theorem. Right, so you've got your upper bound function. That's the green function. That's the one we're calling h. You've got your lower bound function. It's the one we're calling f. And then you've got your weird behaving function in the middle. But since the guy above him goes to this point and the guy below him goes to this point, the middle guy has no choice but to also go to that point. That's what the squeeze theorem says. In practice, we use this to calculate limits of functions that are badly behaved. And I will show you some examples of stuff like that next time, stuff like the sine of 1 over x. It's very badly behaved near 0. You'll see what I mean, right? He oscillates really, really fast as you get closer and closer to 0. So how on earth could we try to figure out what the limit as x goes to 0 of this guy is? Well, he turns out to not exist. But if I smack an x squared on the outside, still lots of really, really weird oscillations in here. Still really hard to work with, but he's bounded above by x squared, and he's bounded below by the negative of x squared. And so the squeeze theorem here will allow us to say what the limit is as x goes to 0 for this function. So that is where I'm going to have to leave it today because of our time constraints. Please take the time to write down this theorem, the policeman or squeeze theorem. And if you have questions about graphing rational functions, send me a Canvas message. I will search around for some good resources for you there. Make sure you finish up homework 1. So I did go ahead and grant, I think there's just 1 or 2 extension requests in there so far. If you haven't finished homework 1, go ahead and request an extension. There's a button in WebAssign that says request an extension. I'll go ahead and grant that. And then your second homework is going to open in just a little bit here this afternoon. Any last minute questions for me?
No, sir. Thank you. Have a great day.
Of course. Yeah, remember, I'm not going to have my normal office hour this afternoon. I have to take my cat to the vet, but I am reachable via email or Canvas messages if you need to talk about anything. And I will be adding a new office hour this week. I just haven't decided exactly when yet. So I will let you know about those things on Wednesday morning. I'm going to go ahead and turn off the screen share and end the meeting. If you could, before you leave, just type here in the chat so I have a record of attendance. And then once you've done that, you're welcome to sign out. Thank you. Yeah, I think she's going to be okay. She was outside the other day and she came back in with this really bad limp and she's been howling like she's in pain. I think she might have sprained or maybe even broken something, but she's going to be all right. I appreciate the concern. Okay. Now I need to get the Calc 2 one ready. All right, so I think pretty much everybody, thank you, has gone ahead and acknowledged in the chat. So I'm going to end the meeting and I hope you guys have a lovely day. And thank you for your wishes about my kitty.